Hi, Chris Good here. This is a video solution to practice ANOVA problem number 2. This is the independent groups ANOVA. So let's check out the question. This is number 2, states history. Students completed a high school senior level standardized U.S. history exam. Major for students was also recorded. Data in terms of percent correct should be R recorded below for 32 students. Compute the appropriate test for the data provided below. I've done a couple of things in advance to speed the video along. Number 1, I've gotten the totals already for each one of our 4 major groups: education, business management, behavioral social science, and fine arts. I've also calculated the sums of squares over here for each one of these individual groups. So when we do our within treatment sums of squares, we're just going to have to add all these up. If you've done this by hand, I'm pretty sure these are right because I double checked it in Excel. So for sum of squares education, 2507.875, sum of squares business management, 3186.875, sum of squares for behavioral social sciences was 3333.5, and for the fine arts was 3270. So we want to find out whether people perform differently on their U.S. history exam based on their major. Okay, let's do all the steps in order. So step 1 is going to be state the null hypothesis. The null hypothesis here is that major has no effect on your history exam score. So that means the mu for the first group is equal to the mu for the second group, is equal to the mu for the third group, is equal to the mu for the fourth group. Or mu for education is equal to business management, behavioral social sciences equal to that of fine arts. All of them are equal. Step number 2 is to find out what our critical value is. I'm going to use an alpha of 0.05. And that critical value, remember F is always a one-tailed test, our critical value is going to depend on 2 types of degrees of freedom. The first is the degrees of freedom between treatments, which is the number of groups you have minus 1. We have 4 different groups, minus 1 equals 3. So in the numerator, degrees of freedom are going to be 3. The degrees of freedom within treatments is going to be equal to big N, the number of scores that we have, minus K. Now we have 1, 2, 3, 4, 5, 6, 7, 8 scores in 4 groups, so N is equal to 32, right? 32 minus K, we have 4 groups, and so 28 is degrees of freedom in the denominator. So now all we have to do is go to our F table. I have one open here on my iPad. And if we have 3 degrees of freedom in the numerator and 28, we have to go on to page 2. 3 in the numerator and 28 in the denominator. At an alpha 0.05, the critical value is 2.95. 2.95 is our F crit. Okay. Step 3, then, is going to be to calculate your test statistic. I'm going to start with the denominator first. So I need sum of squares within treatments. Sum of squares within treatments is just the sum of the sums of squares for each treatment, right? And I already calculated those over here. So I'm going to add 2507.875 plus 3186.875 plus 3333.5 plus 3270. I had already calculated all these out. Let's add these all up. 3270 and 3333.5 and 3186.875 and 2507.875 is 12298.25. Alright, that's our sum of squares within treatments. To get mean squares within treatments, which is the variance, variance is always sum of squares over degrees of freedom. So 12,298.25 divided by, we already said we had 28 degrees of freedom, gives us MS within treatments of 439 point, we're going to round up to 0.22. Alright. We also need the sum of squares between treatments. And that's equal to the sum of your t-squares over n for each group minus g squared over big N. Didn't get g, but I can get that. Our g is our grand total, and that is the sum of all the t's. 453 and 425 and 442 and 452 should be 1772. I'm going to need g squared, so I'm going to write that down up here too. That's 319, what? I missed a digit. 3139984. Alright. Okay, let's do our t-squares over n here. Alright, that's equal to 453 squared over n, which is 8. 425 squared over n, 8 in each group. 442 squared over 8, and 452 squared over 8 minus 1772 squared over n. The total for all of these was 32 because we have 32 squares. Okay. Let's get through this. 453 squared is 205,209 over 8. 425 squared is 180,625, right, over 8. 442 squared is 195,364. Divide that by 8. And 452 squared is 204,304 over 8. 772 squared, oops, or 313,9984 divided by 32 is 98124.5. Alright, so we're going to subtract that out at the end. Alright, 205,209 divided by 8 is 25651.125. 180,625 divided by 8 is 22578.125. 195,364 divided by 8 is 24420.5, and 204,304 divided by 8 is 25538. Don't forget to subtract 98124.5. Okay, let's add them all up. 25651.125 plus 22578.125 plus 24420.5 plus 25538. That's 98187. 98187.75 minus 98124.5 is 63.25. Alright. That is my sum of squares between treatments. We want mean squared between treatments. which is variance. Variance is always sum of squares over the degrees of freedom. It's sum of squares between treatments divided by degrees of freedom between treatments, or 63.25 divided by, what was our degrees of freedom between treatments? 3. So I get 21.08. Now all of this was so that we could get F, which is a ratio of variance. It's the mean squared or variance between treatments to the mean squared within treatments, or 21.08. What was our mean squared within treatments? 439.22. It's going to be small. 0.048 with rounding. Let's compare that to our critical value for F, which was 2.95, so that we can make our decision. Step 4, fail. 2, reject. We'll retain this null hypothesis that we started off with. We don't need to do post hoc tests because we didn't reject the null, and so there's no significant difference among these 4 means, so we don't need to try to find out where it was, because there isn't one. Alright, that's the end of problem number 2.